2 television images. 1. Image elements. Basically, a still image is an arrangement of many small dark and light areas. In photographic prints, fine silver grains provide the differences in light and shade necessary to produce an image, shades. When an image is printed from an engraved image, there are many small black printed dots that make up the image. By looking at the magnified view of Figure 1b, we can see that the printed image is composed of small black and white elementary regions. The basic structure of this image is clear in the portraits in the newspaper. If examined closely, spots will be visible because the image elements are relatively large. Each small area of light or shade represents an image detail or image element. For brevity, these are called pixels or MOPs. All elements together contain visual information on the screen. If these elements are transmitted and reproduced in the same light or shadow levels as the original and in the appropriate positions, then the image is reproduced. As an example, suppose that we want to transmit an image of a black cross on a white ground, on the left in Figure 2 to the right of the image. The image is divided into black and white elementary regions as shown. Image elements in black are white and the pixels that form the cross are black. If each image element is transmitted to the right side of the image and reproduced in its original portion with black or white shading, then the image is duplicated. 2. Horizontal scanning and vertical scanning. The television image is displayed in a row of consecutive horizontal lines, one below the other, as in Figure 3. This scanning allows a video signal to cover all elements of the entire image at one time. The video signal can only show one variation. In order to have one video signal for all light and shade variations, all image details are displayed in sequential time increments. Scanning makes the reproduction of a television image different from that of a printed photo, portrait. In a portrait, the entire image is reproduced at one time. In television, images are reassembled line by line and frame by frame. This time factor explains why a television image can appear with a structure of lines broken up in diagonal segments and frames scrolling up or down the screen. Television images are displayed in the same way as if you were reading a book page to include all the words on a line and all the lines on the page. Starting from the top left in Figure 3, all image elements are displayed in sequential rows from left to right and from top to bottom, one line at a time. This method is called horizontal linear scanning. It is used in the camera tube on the transmitter to divide the image into picture elements and in the picture tube on the receiver to reassemble the reproduced image. The sequence for scanning all image elements is as follows. 1. The electron beam sweeps across a horizontal line, covering all image elements on that line. 2. At the end of each line, the beam returns quickly to the left to begin scanning the next horizontal line. This time to return is called retrace or flayback or blanking. No image information is displayed during trace repetition because during this period, both the camera tube and image tube are emptied. So trace repetitions must be very fast because they waste time with respect to image information. 3. When the file has returned to the left, its vertical position decreases so that the file will scroll the next line down and not repeat the same line. This is done by the vertical scanning motion of the file, which is provided in addition to the horizontal scanning. As a result of vertical scanning, all horizontal lines tilt slightly downward from top to bottom. If the file is at the bottom, repeating the vertical trace returns the file to the top to restart the scanning sequence. The lines of each frame. The number of scanning lines for a complete image should be large to cover the largest number of image elements, and means more detail. However, other factors limit the selection, and this has been standardized at a number of 525 scanning lines for a single image or frame. This is the optimum number of scanning lines per frame for the standard 6 MHz bandwidth of a television broadcast channel. Framework every second. Notice that the beam moves slowly downwards as it scrolls horizontally. This vertical scanning movement is necessary so that the lines are not displayed one above the other. Horizontal scanning produces lines from left to right, while vertical scanning causes lines to fill the frame from top to bottom. The time for one complete frame with 525 scanning lines is 1/30th second. Then the image repetition rate is equal to 30 frames every second. For NTSC system, USA. 3. Video signal information. In a video signal, the voltage and current amplitude changes with time, just like an audio signal, but a video signal is related to visual information. An example of a video signal is shown in Figure 4. Consider this signal as a result of scanning and shown in Figure 3 for the image in Figure 2. This video signal shows black and white information for one horizontal scanning line in the middle of the cross. On the left, the information is white. Further information is black for a longer time at the midpoint. Finally, the information turns white at the end of a line on the right of a video signal produced in this manner. For horizontal lines that run across the image, a total of 525 lines form a framework. All 525 lines are displayed in 1/30th of a second, meaning that the frame repeats itself at a rate of 30 Hz. Note that 30 Hz is half the network frequency of 60 Hz in the USA. The amplitude of video signals can have white up for positive polarity and black down for negative polarity, or with opposite polarity depending on usage. Either way, the main effect is that white and black are represented by opposite voltage polarities in an alternating video signal. Figure 2.4 video signal information for one horizontal scanning line. The video signal is reproduced by a camera tube. This pickup tool converts image information in the form of light changes into electrical changes in the video. The camera tube includes a photoelectric image plate to change the light. Also, the electron beam is changed to move across the image plate to reflect all image elements. In fact, the waveform in Figure 4 is for a camera signal. Video signals are a means by which image information can be carried from one location to another. The basic requirement is to get image information from the camera output to the picture tube input. Common methods include 1. Closed-circuit television, CCTV. 2. Video recording on magnetic tape and recording discs. 3. Television broadcasting. 4. Cable television. 5. Satellite television. The first method uses a basic frequency, baseband, video signal directly, without modulating a radio frequency, RF, carrier wave. Others require a modulated RF signal. A. Motion pictures with all image elements in a television frame using a scanning process. It is also necessary to present the image to the eye in such a way that every movement in the scene can be seen on the screen as a continuous smooth change. In this respect, television systems are very similar to moving pictures. Figure 5 shows a strip of motion picture film. Notice it consists of a series of still images with each a slightly different image framework than the previous one. Each frame is projected individually as a still image. However, the frames are considered one after another in rapid succession to produce an illustration of continuous motion. In commercial motion pictures, 24 frames are shown on the screen for every second that the film is projected. A shutter in the projector rotates in front of the light source. This shutter allows light to be projected onto the screen when the film frame is stationary, but clears any light as the next film frame moves into position. As a result, On the screen you can see a series of still frames of the film. The only time you see a movie is when you are not moving. Figure 2.5. Frames still images in strips motion picture film. Cinema, persistence of vision. The impression made by any light visible to the eye persists for several seconds after the source of light is removed. Thus, if at intervals maintaining this view many views are presented to the eye, then the eye will collect them and the observer has the impression of seeing all the images at the same time. This is a persistence effect that allows television from one basic image element at a time. If these elements are paid off quickly enough, they become a complete picture. Besides that, to create the illusion of movement, quite complete pictures are shown in every second. This effect can be achieved by having an image repetition rate greater than 16 per second. The repetition rate of 24 images per second used in live imaging or cinema is sufficient to produce the illusion of motion on the screen. Kepid, flicker in live images. However, the rate of 24 frames per second is not fast enough to allow the brightness of one image to mix smoothly with the next one when the screen frames are black. The result is a limited amount of light flickering when the screen is alternated between light and dark. This flickering looks worse at higher levels. In motion picture films, the problem of flicker is overcome by running the film with a projector at a rate of 24 frames per second but showing each frame twice so that each second represents 48 images. A shutter is used to clear the light from the screen not only when each frame changes but also alternately. Then each frame is projected twice on the screen. During each second there are 48 views of the scene, and the screen is blank 48 times each second even though there are still the same 24 frames in each second. As a result of the increase in discharge rate, the flickering disappears. 5. Frame and field frequencies. A process similar to motion picture film is used in television to reproduce motion in scenes. Not only is each image cut up into many individual image elements, but also the screen is screened quickly enough to provide enough complete images or frames every second to give the illusion of movement. However, instead of the rate of 24 frames per second used in commercial motion picture practice, the frame repetition rate is 30 frames per second in television systems. This repetition rate provides the necessary continuity of motion. The image repetition rate of 30 per second is still not fast enough to overcome the flickering in the light levels produced by the picture tube screen. Again, the solution is similar to that of the moving image. Each frame is divided into two parts, so that 60 views of the scene are presented to the eye during each second. However, the division of a frame into two parts cannot be done simply by a light controller as in film, because in television, the image is reproduced one element at a time. On the other hand, the same effect is obtained by interlacing horizontal scanning lines in two groups, namely one with odd-numbered lines and the other with even-numbered lines. Each group of odd or even lines is called a field. The repetition rate of the fields is 60 per second, because two fields are paid during a frame period of seconds. In this way, 60 image views shown for 1 second. This repetition rate is precise enough to eliminate flickering. A frame repetition rate of 30 was chosen in television because most homes in the United States are equipped with 60 Hz alternating power. If the frame rate is 30 per second, the field rate is equal to a mesh frequency of 60 Hz. In countries where the mesh frequency is 50 Hz, the frame rate is 25 Hz, which makes the field frequency 50 Hz. 6. Frequency of horizontal and vertical scanning. A field rate of 60 Hz is the vertical scanning frequency. This is the rate of speed at which the electron beam completes its cycle of vertical motion from top to bottom and back again to top. Thus, The vertical deflection circuits for either the camera tube or picture tube operate at 60 Hz. Time of each cycle vertical scanning for one field is 1/60th second. The number of horizontal scanning lines in a field is half the number of 525 lines for a complete frame, because one field contains every other line. This provides 262.5 horizontal lines for each vertical terrain. Since the time for the field is 1/60th second and since it contains 262.5 lines, the number of lines per second is 262.5 times 60 equals 15,750, or assuming 525 lines for a pair of consecutive fields, which is a frame. We can multiply the frame rate by 30 times 525, which results in the same 15,750 lines being paid in 1 second. This frequency of 15,750 Hz is the rate at which the electron beam completes its horizontal motion cycle from left to right and back again to the left. Thus the horizontal deflection circuits for one of the camera tubes or picture tubes work at 15,750 Hz. Time for horizontal lines. The time for each horizontal scanning line, h, is 1/15,750th of a second. In microseconds, time h equals 1 million divided by 15,750 microseconds equals 63.5 microseconds, approximate. This time in microseconds shows that the video signal for image elements in horizontal lines can have high frequencies, namely in the order of megahertz. Note that the frequency f is equal to 1t. If there are more lines, the scanning time will be shorter, which results in higher video frequencies. Actually, in our system of 525 lines, the highest video frequency is limited to close to 4 MHz due to the 6 MHz limitation for commercial television transmitter channels. A. Horizontal and vertical alignment. The time spent in scanning is related to the distance in the image, shadow. As the electron beam in the camera tube scans the image, it covers the different elements and provides appropriate image information. Thus, when the electron beam hits the image tube screen at the receiver, scanning must be timed correctly to get the image information in the right position. On the other hand, the electron beam in the picture tube may screen the part of the screen where a person's mouth would be when the image information is received at a time suitable for the person's nose. To keep the transmitter and receiver scanning in line, special alignment signals must be sent along with image information to the receiver. These timing signals are square pulses that are used to control both camera and receiver scanning. Alignment pulses are emitted as part of the complete image signal to the receiver, but they occur during the blanking time. When no information is emitted, the image is blanked in this period while the electron beam is repeating the trace. A horizontal alignment pulse at the end of each line determines the start of the horizontal trace repetition. Note that the alignment is at the start of the trace loop or the end of the trace, and not at the start of the trace. Repetition of the horizontal trace of the scanning electron beam starts from the right of the image. The vertical alignment at the end of each terrain determines the start of the vertical trace repetition. At this time, the scanning electron beam is at the bottom of the image. Without vertical field alignment, the image reproduced on the receiver does not persist vertically. He scrolls up or down on the picture tube screen. If scanning lines are not aligned, the image does not hold horizontally. It slides left or right and then dismembers into diagonal segments. In summary, the horizontal line scanning frequency is 15,750 Hz. The frequency of the alignment pulses is also 15,750 Hz. The frame repetition rate is 30 per second, but the vertical field scanning frequency is 60 Hz. The frequency of the vertical alignment pulses is also 60 Hz. Note that the scanning frequencies of 15,750 and 60 Hz are appropriate for monochrome televisions but only approximate for color televisions. In color transmission, the horizontal line scanning frequency is exactly 15,734.26 Hz and the vertical field scanning frequency is 59.94 Hz. These precise scanning frequencies are used to minimize interference between additional color carrier signals at 3.579545 MHz and luminance signals, 1 color. This technique is explained in Chapter 8, Color Television Circuits and Signals. However, the horizontal and vertical scanning frequencies can generally be considered 15,750 and 60 Hz because the deflection circuits are automatically aligned to the scanning frequency required for both monochrome, 1 color, and color broadcasting. B. Horizontal and vertical emptying. In television, blanking means going black. As part of the video signal, the discharge voltage is at black level. The video voltage at black level interrupts the beam current in the picture tube to clear light from the screen. The purpose of these blanking pulses is to make the required repeat trace invisible in scanning. Horizontal pulses at 15,750 Hz blank repeat traces from right to left for each line. Vertical pulses at 60 Hz blank trace repetitions from bottom to top for each field. The time required for horizontal emptying approaches 16% of each horizontal line, h. The total horizontal time is 63.5 microseconds, including tracking and repeating traces. Then the discharge time for each line is 63.5 times 0.16 equals 10.2 microseconds. This clearing time h means that the trace repetition from right to left must be completed in 10.2 microseconds before the start of visible image information during scanning from left to right. The time to vertical emptying, v, is approximately 8% of each field v. Total vertical time is seconds. This blanking time v means that within 0.0013 seconds the repetition of the vertical trace must be complete from the bottom to the top of the image. Trace repetition takes place during the blanking time due to scanning alignment. The alignment pulses determine the start of trace repetition. Each horizontal alignment pulse is inserted in the video signal during the time of the horizontal alignment pulse. Also, each vertical alignment pulse is inserted within the video signal during the time of the vertical alignment pulse. In summary, first a blanking pulse puts the video signal at black level. Then the alignment signal starts repeating the trace in scanning. This sequence applies to both blanks, namely horizontal and vertical trace repetitions. 2 to 9 color signal 3.58 MHz. The color television system is the same as monochrome except that color information is also used in this scene. This is done by looking at the image information expressed in red, green and blue. When the image is displayed on the camera tube, separate video signals are produced for the red, green and image information. Blue, colored optical filters separate colors for the camera. However, for broadcasting on a 6 MHz television channel, the red, green and blue signals are combined to form two equivalent signals, namely one for light and the other for color. Specifically, the two signals transmitted are as follows. 1. Luminance signal. This signal only contains variations in the brightness of image information, including fine details such as in single color signals. Luminance signals are used to reproduce black and white or monochrome images, usually called Y signals, not yellow. 2. Color signal, chrominance signal. This signal contains color information and is emitted as modulation on an additional carrier, subcarrier. The exact frequency of the additional carrier is 3.579545 MHz, which is generally considered to be 3.58 MHz. Thus 3.58 MHz is the frequency for color. Generally it is called signal C for chrominance or chroma. In a color television receiver, the color signal is combined with the luminance signal to retrieve the original signals, namely red, green and blue. Then these signals are used to reproduce color images on the screen of a color picture tube. This color screen has phosphors that produce red, green and blue. All colors can be produced as a mixture of red, green and blue. A typical color television image is shown on color plate I in monochrome receivers. The Y signal produces a black and white image. The 3.58 MHz color signal is still not used. As a result, color and monochrome systems are completely equivalent. When a program is televised in color, the image is reproduced in color by color receivers and in black and white by monochrome receivers. Moreover, programs televised in monochrome are reproduced in black and white by both monochrome and color receivers. Three-color picture tubes can also produce by combining red, green, and blue. Note that the color information starts with red, green and blue on the camera and ends with red, green and blue on the picture tube, because these colors are the main colors for television. 2.10. Image quality. Assuming it is aligned to stills, the reproduced image will also have high brightness, strong contrast, sharp details, and an appropriate ratio of height and width. These requirements apply to both color and monochrome. Besides that, color images should have strong colors or saturation, with the right paint or pattern. Brightness of light. Brightness, lightness, is the average or total illuminance intensity, and determines the basic level in the reproduced image. Individual image elements can vary above and below this average light level. The light on the screen depends on the amount of high voltage to the picture tube and the direct current bias in the cathode grid circuit. In television receivers, light control changes the direct current bias of the picture tube. The fluorescent screen of the picture tube illuminates only one small spot at a time. So the brightness of the complete image is much lower than the actual spot illumination. If the screen is wider, more spotlight is needed to produce sufficient light. Contrast. By contrast we mean the difference in intensity between the black and white parts of the reproduced image. The contrast range should be large enough to produce a strong image, with bright whites and dark blacks for extreme intensity values. The number of alternating video signals determines the contrast of the reproduced image. The amplitude of an alternating current signal determines how strong the white color is compared to the black parts of the signal. In a television receiver, the contrast controller changes the peak-to-peak amplitude of the alternating video signal coupled to the cathode circuit of the picture tube. In fact, black in the picture is the same level of light you see on the picture tube screen when the television is closed. In an image, this level appears black versus white fluorescence. However, black cannot appear any darker than the room light reflected from the picture tube screen. So the ambient illuminance must be low enough to make black appear dark. At the opposite extreme, the image appears distorted with little contrast when viewed in direct sunlight because so much light is reflected from the screen, which makes it impossible to have deep blacks. Details. The quality of detail, also called resolution or definition, is linked to the number of image elements that can be reproduced. With many small image elements, the fine details of shading are clear. Thus, it is best to reproduce as many image elements as possible to create an image with good resolution. This quality makes the image clearer. Small details can be seen, and objects in the image are displayed sharply. Good resolution also provides clear depth to images by producing basic details. The quality of an image that is improved with more details can be seen in Figure 2-6, which shows several more image elements increasing the resolution. In our commercial television broadcasting system, the image reproduced on the screen is limited to a maximum of close to 150,000 image elements if we count a horizontal and vertical breakdown. Such resolution allows almost the same detail as on 16 mm film. This maximum applies to any frame size, from a small 4 by 3 inch image, 102 by 76 mm, to a projected image 20 by 15 times, 6.1 x 4.6 meters. The reason is that the maximum resolution in a television picture depends on the number of scanning lines and on the bandwidth of the transmission channel. Color levels. In fact, color information is superimposed on top of a monochrome image. How many colors are added depends on the amplitude of the 3.58 MHz color signal. The number of colors or color levels is changed by adjusting the gain or level for signal C in a color television receiver. This controller is called color or color level, chroma. Intensity or saturation. Color control will change the image from no color to pale or medium tones to vibrant and strong colors. Color pattern, hue. What we usually call the color of an object, more specifically, is the pattern or paint. For example, grass has a green hue. In a color television picture, the hue or paint depends on the phase angle of the 3.58 MHz color signal. This phase is related to a color synchronization signal that is changed through a pattern or paint controller. The controller is set to the appropriate shade of any known color in the scene, such as sky blue, grass green or flesh pink. Then all the other patterns are correct for color alignment to hold the patterns in their correct phase. Comparison of aspects. The ratio of the width to the height of an image frame is called aspect ratio. Defaulted to 4:3, this ratio makes the image wider than it is tall by a factor of 1.33. In approach, the same aspect ratio is used in frames in ordinary motion picture films. Making the frame wider than it is tall allows movement within the scene, which is usually in a horizontal direction. Only proportionality is regulated by aspect ratio. The actual frame size can be anywhere from a few square inches to 20 by 15 feet, 6.1 x 4.6 meters, as long as the correct aspect ratio of 4:3 is maintained. If the picture tube does not produce an image of this ratio, a person in the scene looks too thin or too wide. Square picture tube screens have a ratio of close to 4:3 width to height. So if the horizontal scanning amplitude exactly fills the width of the screen and the vertical scanning amplitude exactly fills its height, the reproduced image has the appropriate aspect ratio. View distance. Close up on the screen, we see all the details. However, separate scanning lines can be seen. We can also see the fine grain of the image reproduction. In television, these grains consist of small white spots called snow, which are produced by noise in the video signal. So, the best viewing distance is an agreement, which is around 4 to 8 times the height of the image. Two to 11. 6 MHz television transmitter channel. The frequency group assigned by the FCC to a transmitting station for signal transmission is called a channel. Each television station has a 6 MHz channel in one of the following frequency areas, bands, allocated for commercial television broadcasting. 1. VHF low-frequency field channels 2 to 6 from 54 to 88 MHz 2. VHF high-frequency field channels 7 to 13 from 174 to 216 MHz 3. UHF channels 14 to 83 from 470 to 890 MHz in all these frequency fields. The width of each television channel is 6 MHz. For example, Channel 3 broadcasts at 60 to 66 MHz. The RF carrier signals for image and sound are both included in each channel. Video modulation. A field width of 6 MHz is primarily required for image carrier signals. The amplitude of this carrier signal is modulated by a video signal with a wide range of video frequencies up to close to 4 MHz. The highest video modulating frequencies from 2 to 4 MHz correspond to the smallest horizontal details in the image. Color modulation. For color broadcasting, the 3.58 MHz color signal contains color information. This color signal is combined with the luminance signal to form a single video signal that modulates the image carrier wave for transmission to the receiver. Sound FM. Also included in the 6 MHz channel are sound carrier signals for images, which are called associated sound. The sound carrier is an FM signal that is modulated by audio frequencies in the range of 50 to 15,000 Hz. This audio frequency range is the same as for stations in the commercial FM transmitter frequency range of 88 to 108 MHz. In a TV sound signal, the maximum frequency swing of the carrier is plus or minus 25 kHz at 100% modulation. This swing is smaller than plus or minus 75 kHz at 100% modulation in the FM broadcast frequency field. However, the sound of the television has all the advantages of FM over AM, including less noise and interference. On NTSC systems, carrier frequency. Figure 2.7 shows how different carrier signals fit into a standard 6 MHz channel. The image carrier frequency, designated P, is always 1.25 MHz above the low end of the channel. At the opposite end, the sound carrier frequency designated S is 4.5 MHz above the image carrier signal, or 0.25 MHz below the top end of the channel. This range of carrier frequencies applies to all TV channels in the field of VHF and UHF frequencies, whether the broadcast is color or colorless, monochrome. Note that the image carrier frequency is not in the middle of the 6 MHz channel, because this arrangement allows more room for the upper sidebands of the modulated image carrier signal. To apply standard spacing to actual RF carriers, consider Channel 3 as an example of this entire channel broadcasting at 60 to 66 MHz, which is a frequency field 6 MHz wide. The image carrier frequency is 60 plus 1.25 equals 61.25 MHz. The sound carrier frequency is 66 to 0.25 to 65.75 MHz. Intermediate carrier for sound, intercarrier sound. The RF sound carrier can also be described as 4.5 MHz above the image carrier because these two frequencies are always separated by exactly 4.5 MHz. This frequency difference is important because all television receivers use 4.5 MHz for intermediate frequency sound signals. The 4.5 MHz signal is called an intercarrier sound signal. At the receiver, the sound signal is made to have a beat frequency with the image carrier, so that the frequency difference is always exactly the same as 4.5 MHz. The intercarrier sound method makes it much easier for the receiver to tune the sound combined with the picture, especially for UHF channels. Note that 4.5 MHz sound is still an FM signal with original audio modulation. Transmission standards mainly because scanning must be synchronized for proper operations. The receiver depends on the transmitter. Thus it is necessary to establish transmitter standards, so that a receiver will work equally on all stations. The FCC has established a list of broadcasting standards. Several points in the standard are mentioned here to briefly summarize the main requirements of a television system. 1. It is standard to pan at a uniform speed in horizontal lines from left to right, continuing from the top to the bottom of the image when the scene is viewed from the camera position. 2. The number of scanning lines for each frame period is 525. 3. The frame repetition rate is close to 30 Hz, or to be precise it is 29.97 Hz. 4. The additional carrier signal for color has an exact frequency of 3.579545 MHz. 5. The aspect ratio of the framework is 4 horizontal units and 3 vertical units, or 1.33. 6. The channel width specified for a television transmitter is 6 MHz. This field width applies to VHF and UHF channels, for monochrome or color. 7. The amplitude of the image carrier signal is modulated by the image signal and the alignment signal. They have different amplitudes on the transmitted AM image carrier. AM transmitters for image signals are called visual transmitters. 8. The sound included is transmitted as an FM signal. Maximum frequency swing is plus or minus 25 kHz at 100% modulation. The sound carrier frequency is 4.5 MHz above the image carrier frequency in the 6 MHz broadcast channel. FM transmitters for sound signals are called audible transmitters, oral transmitters.